Last time I presented this proposition about the normal Jacobi fields along a geodesic gamma. What we want to do next is to describe the structure of the set of Jacobi fields along a geodesic gamma, that is the space I denoted by J gamma. Precisely if J tangent gamma is the space of tangential Jacobi fields along gamma, and J orthogonal gamma, this is a space of normal Jacobi fields along gamma. We can prove that J gamma can be written as the direct sum of J tangent gamma and J orthogonal gamma. And it holds true that dimension of J tangent gamma is exactly 2. Instead, dimension of J orthogonal gamma is 2 times n minus 1. In order to prove this result, we will use this proposition. Precisely, we will use the equivalence between A and C, combined with the fact that we know that there exists an isomorphism defined by this map where J is a Jacobi field, of course. So this is an isomorphism between J gamma and T gamma A M plus T gamma A M. More precisely, the result I want to prove is this corollary. So if gamma is a non-constant geodesic, in M, where M is a Riemannian manifold, then dimension of J orthogonal gamma is equal to 2 times n minus 1. Dimension of J tangent gamma is 2. And every Jacobi field can be decomposed uniquely as a sum of a tangential Jacobi field and a normal Jacobi field. So let's fix A in I, the interval on which gamma is defined, and let's use the isomorphism I mentioned before. So the proposition I erased, the one I presented last time, says that J orthogonal gamma, this is the preimage of the subspace of pairs VW with VW in T gamma A M, such that V orthogonal to gamma prime A and W orthogonal to gamma prime A. Clearly, this is a subspace of dimension 2n minus 2, then dimension of J orthogonal gamma is 2n minus 2. The reason why the dimension of this subspace is 2n minus 2 is that we work with vectors which are with two vectors which are orthogonal to gamma prime A. This means that we have two relations, and consequently the number of freedom degree decreases by 2. And of course the number 2n comes from all the possibility you have for choosing V and W. The choice of V and W depends on 2n parameters, so you decrease this number by 2 and you get the dimension. On the other side, what can we tell about J tangent? We know that this space contains J0 and also J1, where J0T is gamma prime T, J1T is the Jacobi field given by this formula, and it's clear that they are linearly independent, and this follows from the fact that gamma prime T is never zero because gamma is a geodesic. We have also that J tangent gamma intersection J orthogonal gamma intersection J tangent gamma, this is empty, actually contains zero, sorry, I made a mistake. So this implies that the dimension of J tangent gamma is exactly 2, and we have the decomposition I announced a few minutes ago, that is J gamma is J orthogonal gamma direct sum J tangent gamma, and this implies that any element of J gamma can be decomposed as the sum of a tangential Jacobi field and a normal Jacobi field. Now we focus our attention on Jacobi fields vanishing at one point, and our goal is to prove that there is a formula for Jacobi fields in constant curvature manifolds, and later we will use this formula for proving the formula for constant curvature matrix in normal coordinates. The first result I present is a lemma which says the following. Suppose that gamma is as usual a geodesic in a Riemannian manifold with 0 in I. Suppose that J suppose that J is a Jacobi field along gamma such that J0 is 0, then if M is geodesically complete or I is compact, then J is the variation field of gamma st equal exponential map at t of t times v plus sw where p is a gamma 0, v is a gamma prime 0, w is a dt j at 0. I don't prove this lemma. It's very easy. The proof, I just tell you that you have to use this formula where sigma s is a curve and vs is a vector field along sigma s, making the appropriate choices for sigma s and vs. So this is the general formula that you have to use when you have a Jacobi field and you want to find the variation of which J is the variation field. So this proposition tells us how the Jacobi fields which vanish at a point look like. So suppose, as usual, that this is a geodesic. With 0 in I, we set P to become 0. Then for every W in TPM, the Jacobi field along gamma, let's write also the name J along gamma, such that J at 0 is 0, dt J at 0 is W, is given by this formula. Differential of the exponential map at TV acting on TW, where V is gamma prime 0, and we regard T times W as an element of this tangent space. By identifying this space with TPM. And last, if x1, x2, xn are normal coordinates on a normal neighborhood of B, containing gamma I, then J can be written as TWI delta I restricted with gamma T, where W is WI delta I at 0. So if you want to prove this result, we use the previous lemma. So we have that J is the variation field of the variation through geodesic gamma ST equal to this formula. And if you want to get this expression for J, you have to compute Jt equal to this derivative. What about this formula? Simple. You use again the expression of the variation in normal coordinates. So in normal coordinates, we have that gamma st is t, I don't need this, t times v plus s w, where this is a compact version of t v1 plus s w1, t v2 plus s w2, t vn plus s wn, and it is clear that these formulas comes from the fact that when you have a geodesic, then in normal coordinates this geodesic becomes tz1, tz2, tzn. And once again, if you want to get j, you take derivative with respect to s of this formula and you evaluate at 0t. A corollary is the following. Suppose that U is a normal neighborhood of P, then for each Q in U different from P, then every vector in TPM is the value of a Jacobi field J along a radial geodesic such that J vanishes at P. Okay, maybe we can see the proof because it's very short. So if we fix a point Q in U minus P, and W is a vector in TQM, sorry, I made a typo here. This is Q. I apologize for the inconvenience. So suppose that W is this vector, then we know that a curve of this kind is a geodesic, which is a radial, and we have clearly that gamma 0 is P, gamma 1 is Q. Then we can use the previous proposition, precisely this formula, for the Jacobi field along gamma, and it is clear that J0 is 0, J1 is W. So we can construct a Jacobi field which for t equal 1 is equal to the value of an arbitrarily chosen vector of TQM. Now, as I announced at the beginning, I want to talk about Jacobi fields in constant curvature Riemannian manifolds. In order to do this, I will need to introduce some notation. C denotes a number in R, and SC is a function defined by this formula. So the proposition I would like to prove says that if Mg has a constant sectional curvature C, and gamma is a unit speed geodesic in M, then the normal Jacobi fields along gamma vanishing at t equals 0 have the form Jt equal k times SCT ET, where K is a constant arbitrarily chosen. E represents a parallel unit normal vector field along gamma, and SC is a function I defined 1 minute ago. It is also possible to write down a formula for the initial derivative of jt we have that dtj at 0 is k e evaluated at 0, and the norm is given by this formula: absolute value of SC times the norm of the initial derivative. So by hypothesis, the Riemannian manifold has a constant section curvature. So we have that the curvature endomorphism is given by this formula. Then the Jacobi equation dt square j plus r j gamma prime equals 0 becomes dt square j plus c gamma prime j minus j gamma prime, and this is 0, but by hypothesis this is 1 and this is 0 because we are looking at normal Jacobi fields. So this becomes dt square j plus cj. So this formula says that the second covariant derivative of j is parallel to j. Then an idea that we can use to find a solution is to set j of t as, to define j of t as a vector field parallel to a parallel unit normal vector field E. But if we replace J by U times C into this formula, and using the fact that E is parallel, then we get U second T plus C U T equals 0, that we know how to solve. So precisely if U0 is 0, then UT are KSCT. Or let's say, okay. So, so this way we get all the normal Jacobi fields which vanish at 0. And this is a space dimension n-1, so consequently the space of parallel normal vector fields has the same dimension. Now if you want to prove the other statements, you compute Tj at 0 using this formula and this formula. So you will get K S C prime 0 is 0, and by definition this is equal to 1, so this is K is 0. Consequently we have that Tj at 0 as a norm equal to the absolute value of K, because this is of norm 1. Consequently, you get from here a norm of J equal times dtj at 0, because this is equal to K, and E does not appear because it is parallel and it has norm 1. Now, in order to prove the formula for constant curvature matrix in normal coordinates, I need to introduce some definition. So let pi to be the map defined on Rn minus the origin with values in Sn minus 1, given by this formula. Then we can define G hat as the pullback of the standard metric on this sphere. Then it's easy to prove that this lemma holds true. So on Rn minus the origin, we have that the Euclidean metric G bar is given by this formula. G bar equal dr square plus r square G hat, where r of x equal length of x is the Euclidean distance from the origin. So I leave the details of this proof to you. Instead, I prefer to talk about this theorem. Suppose that Mg is a Riemannian manifold with constant sectional curvature C, given P in M, let x1, x2, xn be normal coordinates on a normal neighborhood U of P let G hat equal the pullback of G circle, then on U minus P the following formula holds true. G equal dr square plus SCR square G hat. So suppose that G bar is the Euclidean metric and GC is dr square plus SC r square G hat. So we know that if we use normal coordinates, the radial vector field delta r by the Gauss lemma is orthogonal to the level sets of the function r. So this is Gauss lemma. And this is true with respect to G hat GC. So this sentence means that G of delta R W equals 0, G bar delta R W equals 0, GC delta R W equals 0 if W is tangent to the level sets, let's say to a level set of R. What about the product of two tangent vectors? So suppose that W1, W2 are tangent to a level set of R. It is true that GW1 W2 is equal to GC W1 W2. In order to prove that, we use the polarization formula. In other terms, you know that if you have a metric, then GW1 W2 can be written this way. And a similar formula is true for GC. And then it's enough to prove that GWW equals GCWW with W tangent to a level set of R. So suppose that W is tangent to the level set R equal B, then if you compare GC equal dr square plus SCR square G hat and G bar equal dr square plus R square G hat, we can write GCWW equal SCB square G hat WW, and this is equal to SCB square over B square G bar WW. Now suppose that Q lives in U minus P, W is in TQM, and W is a tangent to the level set of R containing Q. Then if B is the distance with respect to the metric G between P and Q, then this map is the coordinate representation of a radial unit speed geodesic joining P to Q. Now let's suppose that J is an element of key of gamma given by the formula Jt equal T over B Wi delta I restricted to gamma T, where Wi delta I at Q is the representation of W. Now we use the proposition so the proposition about Jacobi field vanishing at a point is a number 10.10, correct? 10.10. That dTj at 0 is 1 over b wi delta I at p, and J is a Jacobi field. And from the definition, it is clear that J at P is W. Now J is orthogonal to gamma prime at P and Q. And this means that J is normal. We have seen that if you find that Jacobi field is normal to gamma prime at 2 points, then is normal. Now we use the proposition 10.12 about the Jacobi fields in spaces of constant curvature. And we have the following. The square of the length of W, this is equal to this, clearly. It follows from here. Then from this proposition you get SCB squared times DTJ at 0 squared respect to G. But this the derivative is here. So this is SCB squared times 1 over b squared length of this vector squared. But this vector here, sorry, I mean the square of this length coincide with W, length of W squared with respect to G bar. And by the formula that we got by comparison of the matrix G, C, and G bar, I wrote before G, C, W, W. I get that this is equal also to this. And this is the end of the proof, because we proved that GWW is GCWW. implies G equal GC, because we proved this formula for tangent vectors and for vector having for pair of vectors of this form. The first one is delta r, the second is tangent to the level set of the R function. So this means that G and GC coincide everywhere. Okay, so let me check how much time I have. So now we have this nice corollary. Local uniqueness of constant curvature matrix suppose that mg and m tilde g tilde are Riemannian manifolds of the same dimension with constant sectional curvature C. Then for any P in M, for any P tilde in M tilde, there exist neighborhoods U of P, U tilde of P tilde, and an isometry phi between U and U tilde. So this corollary says that up to an isometry, locally there is only one space with one Riemannian manifold with constant sectional curvature C. So let's prove the result. So suppose that U is a geodesic ball of small radius epsilon containing P. P is a point of M. And U tilde, a geodesic ball of radius epsilon containing P tilde. Let's use normal coordinates on these geodesic balls. So we have two maps. Between the first one between u and b epsilon 0, and the second one from u tilde to b epsilon 0, where b epsilon 0 represent the ball of center 0 radius epsilon in Rn, if the dimension of the manifold is n. If we use these coordinates, then we have that the formula for G and G tilde coincide. It is dr square plus sc square r G hat. On b epsilon 0 minus the origin, and at the origin clearly we have that this is true by construction. Then the isometry is given by psi tilde inverse composite psi. And this is the end of the proof. Another corollary which is always about metrics with constant curvature, and it states that such metrics can be written as warped products. So if Mg is a Riemannian manifold with constant sectional curvature C, U is a geodesic ball of radius B, centered at P in M, then U minus P is isometric to the warped product 0B times Sn minus 1 using the function Sc, where 0b is equipped with the Euclidean metric and Sn is equipped, Sn minus 1 is equipped with the metric G circle. I leave the details of the proof to you. So I think it's a good point where to stop. Next time we will talk about a different topic. Precisely, I will present the notion of conjugate points and we will study their properties. Thank you for your attention.